Yes, hello everyone. Continuation of undamped free vibrations of single degree freedom system. I have chosen two systems already, and both of them belong to single degree freedom systems. Okay, this is one system and this is the other one, and as usual, what is to be followed? The natural frequency. So I shall not go again why we are finding out natural frequency, what is natural frequency. Quickly recall, and you should know any time. Okay, how is the system? You have a pulley, okay, a pulley which has been say pin jointed or hinged as shown here, and its mass is M and its radius is R. Okay, so this is a pulley which can rotate about this point. Maybe I can call this point as the point about which the pulley can rotate. Okay, around the mass of this pulley is M and the radius is R, and you have something what is called as, okay, let me make it white. So here whatever that has been shown in yellow, this is, okay, what I call it as an inextensible string, a belt-like thing, okay, which goes from here to here. This is inextensible. That means it is rigid. Even if you apply force, its length is not going to change. It may be here. So what it means is, if this point goes by certain amount, say, then the same amount this end will come down. That is the meaning. The meaning of inextensible string for our application is, whatever the movement of this in the downward direction, the same amount this point will go up. Okay, that is inextensible string. Then to this one end of the string, a point mass has been attached, and that mass is small m, and this is capital M, the mass of this pulley. Okay, and the other end of this inextensible spring, there is a spring here whose stiffness is K. Okay, this is how the system is. So maybe right now whatever I say is equilibrium position. This is equilibrium position. Okay, so at equilibrium position, so you know that it is inextensible, I shall remove it. And so maybe the wave which is trying to pull it down. And one more thing what we need to assume here, that so this string and this pulley, there is a good contact, enough amount of friction, and there is no slip between this inextensible string and the pulley. So what I mean is, slip means only the pulley rotates and this is not going to move. It is not going to happen like that. There is no slip, there is no relative motion between this and this string. So therefore, if this moves, then the string also is going to move. That also is one more very, very important information. Okay, so at equilibrium, what happens? Okay, the weight mg, what it is trying to do is, it tries to rotate. Mg will pull this inextensible string in the downward direction, but the pulley is not rotating. The pulley is not rotating, or this is not coming. That means there must be some force this side also. So at equilibrium, if I draw the free body diagram of this pulley, okay, what is happening here? There is a weight mg which is acting vertically downwards, and the string here, the tension or the string, there must be some force here also. And so what this mg will try to do? This mg will try to rotate this pulley in the anti-clockwise direction. And what about this? So if I cut it here, I can show tension. Or in other words, and how do you get this? Or in other words, the spring must be pulling it in the downward direction. The spring or the spring shall try to pull it in this direction. This is the force which is coming from that. That is equal to K into delta SE. The The spring must have undergone an extension, and that it tries to become smaller in length, and therefore it is trying to pull it. So therefore mg multiplied by r, I am taking momentum of this point, is also equal to k into delta st into r. R cancels. You have what's called as mg is equal to k delta st. Okay, I don't know whether I need it, whether I use it or not. But this is what is happening in what? At equilibrium condition. Now let me set this into vibration. How? This mass, I pull it down. Say I bring it here. Then you know that this portion also comes down, and it is not going to extend, and therefore it just makes the pulley to rotate, and hence the spring is made to extend. Okay, I just before at equilibrium stage, I just draw one radius line here. I draw one line. Okay, whether it is rotating or not, just to observe for that purpose, nothing else. Okay, so let me assume that this mass has come down. This is at t equal to t. At t equal to t, at any time t equal to t. The mass is here. So I can say that this is what? This is the displacement. The string, inextensible string also will come here. And the mass is having velocity x dot, and the mass is having acceleration x double dot. Okay, so then what happens when this small m comes here? What happens to this line? This line also will rotate, and probably say it might have come here somewhere here. That means this pulley has undergone an angular displacement of theta. And it is reasonable to assume that it is having velocity also, what is called as theta dot. And it is also having what is called as theta double dot, angular acceleration. Okay, when this mass comes down, this also will rotate. If the mass goes up beyond the equilibrium position, then this line will come this side. This mass is going to move like this in our free vibration, and this pulley is simultaneously becoming like this, and the spring will extend, compress like that. Okay, I hope you understand. So when this end has come down, this pulley rotates, and what happens to this end? This end probably might have come here, and the spring will come up here. The spring is up, goes up here like this. So this is, what is this distance? This distance is also x. I hope you understand. This end, whatever is the movement, this end, whatever it comes down, the same amount it has to go. I hope it's clear now, everything. So what is the extension of the spring, etc. All that is clear. Okay, now I shall go and I shall solve this problem by what is called as the energy method. What is energy method? We know that total energy is constant. Total energy. Okay, total energy is equal to constant. What is total energy? It is the sum of kinetic energy plus potential energy is equal to constant. And what is kinetic energy in general? Kinetic energy because of translation. Do you have anything translating? Yes, this mass is there translating, moving along a straight line. Then you have what is called kinetic energy because of rotation. Yes, I have it. Rotation. Rotation also is there. Then this is what is the total kinetic energy. Then potential energy. What is potential energy? Because of position of the mass. Then potential energy in the spring. Energy stored in the spring is also known as strain energy. That is strain energy in the springs. This is equal to constant. Okay, now let me substitute one by one. Kinetic energy because of translation. the mass which has come here, it is having velocity of x dot. So it is having kinetic energy because of translation, which is equal to half m into x dot square, half mx dot square, plus the kinetic energy because of rotation, which is rotating here, the cylinder, the pulley is rotating. Pulley is rotating. So what is the kinetic energy because of rotation? That is equal to half I into omega square. So just like half m into velocity square. The kinetic energy because of rotation is half as it is I about O. This pulley is rotating about point O, I-O into theta dot square. Okay, this is kinetic energy because of rotation. Then potential energy because of the position of the mass. The mass is coming down, you all agree? The mass has come down, therefore its potential energy is minus. So that is equal to mg into how much? How much it has come down? X. So minus mgx. Then plus, what is the potential energy stored in one spring? That is spring. Spring is only one spring there, here. Okay, that is the average force. So what is the spring force at equilibrium? At equilibrium, that is K into delta St. Then what is the spring force in the new position? So in the new position, it has come up here. There is a further extension of x, that is plus K into bracket delta St plus x. This is the new force. This is divided by 2. This is the average force multiplied by the displacement. How much is the displacement? Displacement is x. So therefore, let me simplify this. This is equal to what? This is equal to constant. Okay, let me simplify. Before I simplify, okay, what is, though here you have x and theta. So two variables, and don't jump to the conclusion that it is a 2-degree freedom system. It is not. X and theta, though I have two variables here, they are not independent. Both x and theta are related. What is the relationship? X is equal to r into theta. See here, whatever is this distance now, from here to here. From here to here. This is nothing but x. This much length of the string will come down. This much. So what is this? This is x. And how much is this? This is equal to r theta. X is equal to r theta. So therefore, x dot. Therefore, x dot is equal to what? R into theta dot. So now I would like to replace, okay, or I would like to have only one variable. So x is in most of the terms, I shall retain x. And wherever theta dot is there, I shall replace it. So I shall go back and substitute. What is that? Half m x dot square. Half mx dot square plus half. Okay, I naught, the moment of inertia of the cylinder or of the disc, that is given by, it is a formula which you all are expected to know. Half mass into r square. Half mass multiplied by r square is this thing. So this is I naught and into theta dot. Theta dot is nothing but x dot divided by r whole square. So that is this term. Then minus mgx. So I shall, since I have done it so many times, I can straight write it. Plus first k delta st, 2k delta st divided by 2, k delta st. This is k into delta st into x. So this and this they cancel. And another one, okay, k into x plus half k x square, and whole thing is equal to c. And this term they cancel. Okay, simplify further. This, now what I want to do is, I want to differentiate this with respect to time. Okay, so this is equal to half m into 2x dot into x x double dot. I hope you understand what I have done. I am differentiating with respect to time. Then this plus, this is half as it is. The next half m r square as it is. Okay, so x dot, this 1 by r square, I shall separate it. 1 by r square into x dot square. Differentiation of x dot square, 2x dot into x double dot. Okay, then plus half as it is, k as it is, differentiation of x square, 2x into x dot. This whole thing is equal to 0. Okay, some terms I can cancel here. In this term, this 2 and this 2 I can cancel. In this, okay, I shall cancel this 2 and this 2. This 2 will remain. Okay, this 2 and this 2 I shall cancel. Okay, we shall use some portion of this and then come back. And before x dot here, there is one x dot. Here also I have x dot. Here also I have x dot. Divide both by x dot, and x dot, and x dot. Okay, now let me simplify. What do I have? M x double dot, small m into x double dot. Here half, so this r square also I can cancel. This r square and this r square I can cancel. So this small m, so here capital M by 2 into x double dot. That means small m plus capital M by 2 into x double dot. From these two terms, and plus kx is equal to 0. Okay, simplify this. This is 2m plus the capital M divided by 2 into x double dot plus k into x is equal to 0. So I can straight away write it. Omega n is equal to root of k by m. K is k as it is, m, that is this 2m plus capital M, the whole thing divided by 2, that. So this is the expression for natural frequency of this system. Okay, I hope it's clear. Okay, let me quickly move on. Okay, Anil. So the system is relatively simple here. So I have a cylinder of mass m. I have a cylinder of mass m whose radius is r. Okay. So there is through hole here and I have connected a spring. And this cylinder is allowed to undergo rolling operation. It will roll on this horizontal rough surface. That means it is not going to slide. Please remember, there is no slipping. It undergoes pure rolling motion. That means it rotates and then it can come here and then it will rotate, roll back and go like this. And this is how the vibrations can take place. Okay, so at equilibrium, maybe I shall draw one line. So anything, whenever you have a roller or cylinder, it is better to draw a line at equilibrium position. And then how that line is moving, that you observe, then you will come to know how much it has rotated, etc., etc. So now, at equilibrium, the weight of the cylinder mg is acting vertically downwards. The spring is in the horizontal direction. So the weight will not influence anything, any effect on the spring. The spring has not undergone any extension at equilibrium. I hope you concluded. So spring has not undergone any extension at equilibrium position. In this position, the spring force is 0. That is the meaning. Okay. So now I allow it. Wow. I just roll it. I don't move it, pull it. I just roll it and it has rotated and say it has come here and leave it, then it will go like this, then it will go like this. Okay, at some instant of time, let me assume that this mass, the same cylinder, say is somewhere here. This is at t equal to t. Okay, and say the spring has come up here, and say this distance is what is called as x, and this line probably might have gone here. It is undergoing, it is not sliding. If you slide it here, this line will be here. Okay, and it is not only undergoing this thing, it has translated and it also has rotated. Okay, so this angle, let me call it as say theta. So again, r into theta is equal to x. If this is r, and whatever is this distance, no, that is nothing but x. So r into theta is equal to x. Okay, quickly let me write down what is the total energy, which is equal to constant. It is the sum of kinetic energy because of transmission. It has, yes, this point it has moved here. So I have kinetic energy because of translation. I have kinetic energy because of rotation also. Please remember rotation. Then plus potential energy due to position, plus potential energy due to spring. This is equal to constant. So kinetic energy due to translation, this is equal to half m into x dot square. And kinetic energy because of rotation, half I is nothing but half m r square into theta dot square. So potential energy because of position, the position has not changed, it has moving in the horizontal direction. Therefore, with respect to the earth center, it is at equal distance, and therefore the potential energy because of position is 0, change in potential energy. Then this potential energy in the spring, the initial spring force, equilibrium position 0, plus k into x divided by 2, the average force, multiplied by the displacement x, this is equal to c. Okay, so this is equal to half m into x dot square plus half into half, I shall take it 1 by 4 m and r square as it is, theta dot square. So on the same line, r into theta dot is equal to x dot. Theta dot is equal to x dot divided by r. So theta dot square is equal to x dot square divided by r square plus 0 plus half k into x square is equal to 0. Not 0, it is constant. I have not differentiated it. In the very next step, I shall differentiate r square, I shall cancel. So here, this term and this term I can plug it. This is half m and this is 1/4 m. Half m plus 1/4 m. Half m plus 1/4 m into x dot square plus half k x square is equal to constant. Maybe now I shall differentiate it. Anyway, this term is constant. Let me add this together. The LCM will be 4 and 2 2s are 4. That is 2m plus 1m. This is 3m by 4. It's constant. Differentiating it, 2x dot into x double dot plus half k into 2x into x dot. This is equal to 0. Simplify this 2 cancels and 2 1s are 2 2s are. Okay, so x dot and x dot cancels. So what is remaining? 3m by 2 x double dot. Okay, I shall continue here. 3m by 2 x double dot plus k into x. This is equal to 0. So therefore, omega n is equal to root of k divided by 3m divided by 2. Right. So this is the expression for natural frequency. Omega n, so many radians per second that is normally used. Whenever we use express frequency with omega, it is always radians per second. If I use f for the notation to indicate frequency, then in that case it is always cycles per second, or what is called as hertz. Okay. So I thought of introducing the damped free vibrations, but anyway I shall do it in my next class, and then I also start discussing what is called as damped free vibrations of single degree freedom system. Okay. So that will be the topic, very very important from the examination point of view. I feel that though we have spent so much time on this, still it is not very reliable, or I don't know whether you have gained confidence or not. Therefore, the next topic what we discuss from the examination point of view is very 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 crucial, relatively much smaller, and mechanically we can solve problem, and more of substitution like problems will be there, and therefore very important, don't miss it. We shall quickly discuss that. Okay, all the best.